Next, we're going to introduce a heuristic definition for the definite integral. So recall that we previously discussed indefinite integrals, which are basically the entire family of antiderivatives. Today we're going to look at the definition for the definite integral. So before we get to that, let's just look briefly at a graph of a generic function. So suppose I have some function f of x, and over here it's going to go to negative. So here's f of x. So if we look between 2 points on the x-axis, a and b, and we define the vertical lines x is equal to a and x is equal to b, and look for the region that's bounded by those two lines, the curve y is equal to f of x, and then the x-axis. So we look at this region right here, and we compute its area. So this is typically called the area under the curve. So under the curve, y is equal to f of x, and then between x is equal to a and x is equal to b. With a caveat that if the curve is below the x-axis, it's counted as negative. So if the curve is below the x-axis, we count the area as negative. So the area makes a negative contribution. That's motivated by our example with velocity. If you have a velocity that's less than 0, your position is decreasing instead of increasing, so therefore you subtract that distance from your total change in position instead of adding it to it. If you're moving back and forth, your distance isn't growing indefinitely, it's increasing and then decreasing. So we have this notion of area, and it's literally the area under the curve and above the x-axis, and if the curve is below the x-axis, we count it as negative. So we can say that the definite integral and this is a tentative definition because we'll replace it with a little bit more of a rigorous definition once we develop the theory of Riemann sums. But the definite integral is, we call it the integral from a to b of f of x dx, and this is equal to the area under the curve y is equal to f of x between x is equal to a and x is equal to b. So this is the area in the above sense. In other words, in the sense that if f of x is negative, we count area as negative. So it's really a signed area underneath the curve of f of x. And the symbol for the definite integral is very similar to the symbol for the indefinite integral, except we have what are called endpoints. So we have a lower limit of integration and an upper limit. And when I say lower limit and upper limit, that has nothing to do with limits, as in the limit as x approaches infinity of f of x. It just means the lower endpoint and the upper endpoint. That's probably perhaps better terminology, but it's pretty standard to call them the lower limit and the upper limit, even though they have nothing to do with limits per se. So a and b are the left and the right endpoints of the x-axis. And this, since it's an area and we have a and b as fixed endpoints, the area under the graph is going to be a definitive number. That's why it's called the definite integral. So the area might be 12, which means that the integral from a to b of f of x dx would equal 12. It's just equal to the area under the curve. Notice that the definite integral is not a function of x. Now the indefinite integral, so if we say the integral of f of x dx, that has a completely different meaning. That's the family of antiderivatives. So we would say capital F of x plus c. So if capital F of x is an antiderivative for lowercase f of x, then the indefinite integral is just the antiderivative, or one antiderivative, plus c. So this gives you the whole family of antiderivatives. On the other hand, the definite integral always returns a number. So when you have limits of integration, a and b, that means that you're taking your function and churning out some number. Whereas if there are no limits, it's indefinite and you just get the family of antiderivatives. Now at first you might say, well, how is the area related to the family of antiderivatives? You might already have come up with an answer if you're thinking about how this relates to our previous lecture on velocity, area, and distance. And I'll discuss what the relationship is next. So suppose we have a function f of x, and this function has an antiderivative. So let capital F of x be an antiderivative for little f of x. So i.e. capital F of x prime, so capital F prime of x is equal to little f of x. So little f of x is the derivative of capital F. So the question is, what does this area represent? So we have this area underneath the curve. And so the claim is that the area, and this is a signed area, so if it's below the x-axis it counts as negative, is going to equal the capital F of B minus capital F of A. Just like that. And the reasoning is exactly the same, that the area underneath your velocity curve gives you the total change in your position. It's the position at B minus the position at time A. Right? So we can start the same way. So if we let this be A and this is B, and let's say f of x is constant, well, if f of x is constant and f of x is equal to the derivative, capital F prime of x, well, that means that for every change in 1 unit of x, capital F is incremented by this constant. So let's say this height is, let's call it c. Right? So that means that it's the same deal as if you're driving at 70 miles per hour for 3 hours. 70 miles per hour means that every hour your position is incremented by 70 miles. So since this is capital F prime, which is d capital F dx, it means for every change in x, you get a change in capital of F equal to c. So the area under here, which is c times b minus a, is going to equal the total change in capital F. And we can even do better than that in this example, because we can integrate a constant. So if little f of x is equal to c, let's come up with an antiderivative. Well, I know one antiderivative. How about c times x? Right? The derivative of c times x is just c. So therefore, c times x is an antiderivative for f of x is equal to c. Now, what happens if we compute the difference between capital F of b and capital F of a? Why, we get c times b minus c times a, which is equal to c times b minus a. Now, c times b minus a is, again, the area under the curve. So whenever you have a constant function and you have two endpoints, a and b, the area underneath the curve, underneath that constant value between a and b, is just equal to the total change in the antiderivative. Now, for the same way we extended this from the case of constant velocity to general velocity, we can extend this from a constant function to a general function. So now if we let f of x be wild, that's pretty wild, and we go from a to b, say, well, what does the area under this curve represent? Well, we can look at very, very thin rectangles. And maybe if I choose a very, very thin little interval on the x-axis, maybe the height doesn't change so much, right? Because I've just narrow that interval down so much that unless you're wearing your spectacles, you can't see the change in the y. So it looks like it's constant. Well, that means that the area of this thin little rectangle should equal let's say that's x sub I and x sub I plus 1, it should just equal to capital F of x sub I plus 1 minus capital F of x sub I. So in other words, it's a difference between the right endpoint and the left endpoint, approximately, right? Because the function's approximately constant, so the same result holds that we just saw for the case when you take the area under a constant. It's approximately the value of the antiderivative at the right endpoint minus the value of the antiderivative at the left endpoint. So it's a total change in capital F between those two values. Now, if I do that for all of the intervals, a bunch of really, really thin little intervals, I'm going to add up to the total change, call this one delta F sub I, capital F of B minus capital F of A, and that will equal the area. So we have the area like this. Now, the area we defined tentatively as the integral from a to b of f of x dx, or rather, we defined the definite integral as just the area under the graph. Now, if the area under the graph also is equal to capital F of b minus capital F of a, well, that means the integral of little f of x from a to b has to equal capital F of a, or capital F of b minus capital F of a, which means as long as we can figure out an antiderivative for a function, we can always compute the area under its graph. And moreover, if that function represents the rate of change of another function, we can compute the total change in that other function. So if I'm burning fuel at a given rate, if I'm launching a rocket into space, and I integrate my rate of burning fuel, I get the total amount of fuel that I've burned, and so forth and so forth. So this equation is called the fundamental theorem of calculus. Now, for the rest of this chapter, our goal is to do several things. First of all, we are going to define the meaning of the definite integral much more precisely and rigorously. And before we get to that, we're going to define the meaning of area. What does it really mean to take the area under some weird shape? How do you know what the area is? And so to do that, we're going to use something called a Riemann sum. And the Riemann sum is literally just the sum of the areas of all these tiny little rectangles. So you do a bunch of little rectangles, and you add up their areas, and you get an approximation for the overall area. And then you define the definite integral basically as a limit of Riemann sums. So you do this in a process as you make your Riemann sums thinner and thinner, or the rectangles thinner and thinner and thinner and thinner. The area is going to become a better and better and better approximation of your true area. And in the limit, as you make those rectangles infinitely thin, you actually get something that's equal to the total area. So that's kind of a very quick look ahead at how we're going to define this using a little bit more rigor. And then we're going to do a proof. We're actually going to prove that this integral, in a very slick way, using these Riemann sums, has to give you the total change in the antiderivative. So if you don't buy the heuristic argument, I'll prove it later on in the course. And then we'll start talking about some applications of these. So that is the very exciting beginning to definite integrals and the fundamental theorem of calculus, both of which just described or defined and described conceptually and intuitively using some just the consequence of some fairly simple observations. And we're going to get more in depth into what these things really mean in the subsequent lessons.